Good day to you. I'm Esther Rojas. I'm delighted to have the opportunity to give this lecture on behalf of the Stories Project. The Stories Project is focused on researching and developing energy storage solutions to achieve a sustainable energy scheme in Europe. Among the various energy storage solutions under consideration, one particularly attractive technology is that based on sensible thermal energy. This technology is both cost-effective and highly capable. The focus of this lecture is to have an overview of this technology. Allow me to introduce myself. I obtained my PhD in physics from the Complutense University, Madrid, many years ago. Since 1991, I've been working at CEMAT, the Center for Energy, Environmental and Technological Research. My work has focused primarily on enhancing the heat transfer of various thermal energy systems. My research began with the design and optimization of parabolic trough collectors, and since 2007 I have focused primarily on thermal energy storage systems, particularly those operating at high temperatures or utilizing thermodynamic cycles for power generation. All these studies have been part of national and international projects, and the results have been published in scientific journals. I have had also the opportunity to lecture at various universities on subjects related to applied physics. I've supervised 3 doctoral theses. Firstly, I will begin with a presentation of the organizations I'm affiliated with, CIEMAT and its division Plataforma Solar of Almería. Following this introduction, we will proceed to the more technical part of the lecture, where we will define the critical factors to consider when designing a thermal energy storage system. I will provide an overview of the fundamentals, materials, scheme and configurations of sensible thermal energy storage systems according to the potential applications they can be connected. These applications include domestic heating, industrial processes involving heat demand, and power generations in plants connected to the grid. As previously stated, CIEMAT is the Center for Energy, Environmental and Technological Research of Spain. It is a public research institution that focuses on research, development and innovation related to the various energy sources and their environmental impact. CIEMAT headquarters are in Madrid, and that is also the location of my office. There are 2 additional centers in Soria. One focuses on the development of renewable energy sources, and the other is dedicated to law studies related to environmental issues. Additionally, a center focused on socio-technical studies is situated in Barcelona, and an advanced technologies center primarily dedicated to big data and computational research is located in Extremadura. In the southern region of Spain, the Plataforma Solar of Almería is situated. The Plataforma Solar of Almería, or the PSA, an acronym that stands for the same thing, is the most complete installation of its kind in the world for testing concentrating solar thermal technologies. These concentrating solar thermal technologies play a very important role in the development of commercial long-duration and long-term energy storage, as we will see in this presentation. Energy can be stored in the form of thermal energy in 3 different ways: by changing the temperature of the storage medium, by changing its physical state, or by a reversible thermal-chemical reaction. When a change in temperature occurs, we term this sensible thermal energy. When a change in physical state is observed, We term this latent thermal energy. When a chemical reaction is involved, we term this thermochemical energy. The approach adopted for energy storage determines the type of material to be used. In other words, the properties that are essential in identifying a material as a thermal storage medium. Another important aspect is the system efficiency in delivering stored energy. It is important to note that thermal energy can be transferred via three primary mechanisms: conduction, convection, and thermal radiation. Conduction occurs when heat is transferred within a solid body. The thermal conductivity of the material is a key factor in determining its heat transfer efficiency. A higher thermal conductivity results in more efficient heat transfer. Convection is the mechanism of transferring thermal energy due to the movement of a liquid, so its effectiveness depends on how fast the liquid moves and the property of such a liquid. At higher temperatures, thermal radiation becomes a significant factor, and this mechanism must be taken into account above 500 degrees Celsius. It's based on electromagnetic waves. When designing a thermal energy storage system, it is essential to consider how the system is integrated into the application, how it is connected to the energy source, and how the thermal energy provided during discharging aligns with the specific application. Therefore, the optimal thermal energy storage solution for a given application is determined by the synergy of these three key factors: material properties, efficient heat transfer mechanisms, and system integration. Let us now concentrate on sensible thermal energy storage. As previously mentioned, this process involves a change in temperature. The stored energy density is dependent on the volumetric heat capacity of the material and the temperature change imposed on the material. The figure at the bottom left presents the stored energy of different materials and with several temperature steps in a qualitative manner. As the figure illustrates, for a given temperature step, DT1, material 1 stores a significantly higher amount of energy than material 2 due to its larger volumetric heat capacity. As the temperature step is increased, DT1, the stored energy of material 1 also increases. This means that for a specific material, the energy it can store in the form of sensible heat can be adjusted to have a high energy density by tuning the temperature step. Naturally, this always be within the range of temperatures that the material can withstand, which is usually quite wide. As illustrated in the figure at the bottom right, the stored energy density of 5 different materials is compared. Concrete, represented by brown, and a mixture of nitrates known as solar salt in green are employed in a sensible thermal storage system that undergoes 3 distant temperature changes: 100, 200, and 300. Due to its slightly higher volumetric heat capacity compared to that of the concrete, the stored energy density of the solar salt exceeds that of the concrete for the same temperature change. For both concrete and solar salt, a temperature change of 300 results in stored energy density that are triple those at 100. It is evident from the behavior of this sensible storage media that a temperature change of 200 results in a stored energy density that outperforms the latent storage media in blue typically employed for high temperature applications. Notably, lithium nitrate as a latent thermal storage material exhibit at higher stored energy density. However, this can be achieved through sensible storage by imposing a temperature change of 300 in solar salt, a more than feasible scenario. The materials used as sensible thermal energy storage medium must be stable at the working temperature, which is determined by the application, the energy source of both. In addition to this requirement, and as outlined in the previous slide, it is desirable that the materials have a high volumetric thermal capacity. The maximum economical size of pressurized tanks is limited by the liquid storage material's vapor pressure. Therefore, the material should have as low a vapor pressure as possible. When the storage medium is a solid, ensuring good thermal conductivity is essential for efficient heat transfer without the need for additional heat enhancement methods, which might increase system cost. The table at the bottom of the slide provides values for some of these properties for materials under consideration as sensible storage media. For applications requiring temperatures below 100 Celsius degree, liquid water emerges as the superior material due to its substantial volumetric heat capacity and effective convective heat transfer. For temperatures above 700 degrees Celsius, industrial waste emerges as the optimal choice, while for temperatures in the middle of these two values, most of the materials have a similar volumetric heat capacity but synthetic oil. So in a general approach, looking only at its thermophysical properties, solar salt seems to be a very good candidate as sensible thermal storage medium. In addition, the material should be safe and pose minimal environmental risks, as their cost should be as low as possible. One configuration that might be considered for sensible storage is where materials at high and low temperature are located in the same enclosure, requiring a temperature transition between these two regions. This temperature transition is known as thermocline, thus giving rise to the designation of thermal storage systems that exhibit this configuration. The storage medium might be liquid, solid, or a combination of both. As outlined on another slide, the solid materials under consideration for storage purposes exhibit low thermal conductivity, which can compromise the efficiency of heat transfer. One potential solution to consider is to increase the surface area available for heat transfer between the solid material and the heat transfer fluid. How? By dividing the solid material into smaller pieces of a regular shape, similar to stones, or by using a fixed shape, such as concrete bricks or ceramic spheres. In the event of the thermocline tank being vertical, the hot charging fluid is introduced at the tank upper level, resulting in a displacement of the coldest volume to the tank lower level. As illustrated in the figure at the top right, three different moments of a working vertical thermocline tank are presented. It is presented in blue when the tank is completely discharged. Then thermal energy is added to the tank by means of hot fluid that has been driven to the tank's uppermost point. The transition between the currently hotter upper region, indicated in red, and the lower, colder region, indicated in blue, is evident. Should the entry of hot charging fluid into the tank at the top of the tank be continuous, the movement of the thermocline region to the bottom of the tank will be the result. In the absence of cold volume in the tank, it is said that it is fully charged. Thermal energy then can be used after a certain time without major energy losses, always if the tank is appropriately insulated. An alternative solution is to use a horizontal thermocline tank. As illustrated at the bottom right, the figure depicts a half-charged horizontal thermocline tank. This arrangement ensures that the charging hot fluid enters along the tank axis, displacing the cold volume radially to the largest radius. Systems of the types described here are commercially available for temperatures below 150 and for temperatures above 600. Systems with temperatures in between these two are in operation but in pilot plants. At low temperatures, the primary applications are domestic hot water system and the heating and cooling of buildings. In applications where temperatures are below 100 degrees, water is the most cost-effective medium with the highest heat capacity, resulting in a high energy density. For storage volumes below 1 cubic meter, which is standard for single-family houses and flats, there are numerous designs that allow for effective stratification. The key to effective stratification is to ensure that the thermocline zone is as small as possible. Should a significantly larger storage volume be required, for instance 16,000 cubic meters as in the case with district heating, underground storage pits are required. The walls are composed of concrete and are supported directly by the ground, ensuring stability and functionality. There are several samples of this type in the northern European region, where they are used as seasonal thermal storage, storing the summer solar thermal energy that will be used during winter. In addition, there are some examples of the above-ground tanks with storage capacity below 6,000 cubic meters. The figure at the bottom right is a metallic water thermal storage tank of a similar size, which is connected to a thermal power plant in Berlin. Since the early 19th century, packed bed thermal storage systems have been employed at high temperature as heat exchangers. The systems are used in the glass and metal industries to recover waste heat from the exhaust gases of blast furnaces. In this context, they are known as regenerators. Given that the hot gas inlet temperatures can reach up to 1500 degrees Celsius, the solid thermal storage medium is an arrangement of bricks made of fireproof refractories or ceramic materials of a special quality, such as silica or silica alumina. These materials are capable of withstanding the effects of any corrosive materials entrained into the hot gas. In the context of thermal storage, if the solid medium is brickwork, it is said that the packed bed has a structured filler. If it is placed in a tank with a random arrangement, as when using volcanic rocks, alumina spheres, and so on, it is said that the packed bed has an unstructured filler. If the working temperature of the application is 600 degrees, the heat transfer fluid of choice is typically air at atmospheric pressure. Natural rocks can be utilized in unstructured packed beds with air as a heat transfer medium if the temperature remains below 600 degrees. This approach ensures that the rocks do not undergo degradation. Ordinary Portland cement can also be used as a storage medium in a safe way at temperatures below 300 degrees. There are special concretes such as geopolymer-based and calcium aluminate-based concretes that can withstand higher temperatures and for that are being considered as thermal storage media. If the heat transfer fluid is a liquid, synthetic oil, or molten nitrates, it can also serve the function of storing energy. The images of the right illustrate several pre-industrial prototypes of this kind located from left to right in France, Germany, and Portugal. An alternative option would be to house the hot and the cool media in separate enclosures. This configuration is designated to prevent the thermocline region from causing issues, although it should be noted that may result in increased cost. Since transferring storage media between enclosures is needed, liquids must be used as the storage medium. At present, there are commercial systems in operation that utilize this type of scheme for power generation and industrial processes. These products operate at temperatures ranging from 150 to 600 degrees. When the storage system is charged, the liquid storage medium is heated and transferred from one tank to the other, moving from the cold tank to the hot tank. During the discharge process, the heated liquid is expelled from the hot tank, transferring its energy to the application and then returning to the cold tank. Therefore, in each process, each tank is filled while the other is emptied. The storage capacity is increased by the addition of new tanks. This type of scheme is employed at the commercial level for power generation in concentrating solar thermal power plants. These power plants use a Rankine cycle to produce electricity, similar to nuclear or coal-fired power plants, but using the heat obtained by concentrating solar radiation with mirrors. As illustrated, the solar field is composed of parabolic trough collectors that concentrate solar radiation on pipes. A heat transfer fluid flows through this pipeline, powering the steam generation process and the thermal storage system via a heat exchanger, denoted here by a green box, where the system is charged by the energy provided by the solar field. The storage liquid is heated and transferred to the other tank in red, where it is stored at the highest temperature the solar field can provide. Should the need arise, whether during the night or when there is insufficient solar radiation, the hot liquid stored in one of the tanks can supply the thermal energy the power blocks need to produce electricity. The Andasol power plant in Spain is equipped with a thermal storage system that enables it to generate electricity for up to 8 hours in the absence of solar radiation. Similarly, the CSNP plant in China possesses double the electrical output and operates for up to 10 hours without solar energy. Large capacity thermal energy storage systems in a two-tank configuration are also employed in concentrating solar thermal power plants that utilize tower technology. This technology involves the concentration of solar radiation and at a specific focal point, where the heat transfer fluid is heated to temperatures of up to 600 degrees. Should this heat transfer fluid also be used as a storage medium, as illustrated in the provided scheme, it would be stored in the hot tank after being heated. The power block is always fed by the storage system, thus improving the efficiency of the process as a whole. The image of the left depicts an aerial photograph of the Gema Solar power plant, situated in the southern region of Spain. This innovative facility boasts a thermal storage system that enables it to operate for 19 hours, independently of sunlight. The material currently used in concentrating solar thermal power plants in their energy storage system is a liquid non-eutectic mixture of nitrates, known as solar salt. This material must be maintained at temperatures about 240 to prevent its solidification. Despite its classification as a molten salt, it is important to note that its corrosiveness is not particularly high. Solar salt has a number of key advantages. It is capable of functioning within a temperature range that aligns closely with the requirements of efficient Rankine cycles for electricity production. It possesses a high thermal capacity and low vapor pressure, eliminating the need for pressurized tanks. And it is a safe material with a minimal environmental impact. The numerous pilot projects worldwide provided the companies involved in the construction and management of concentrating solar thermal power plants with the required confidence to install this type of energy storage systems. Thermal energy storage system utilizing solar salt in a two-tank configuration are long-term and long-duration commercial energy storage solutions with electrical storage capacity of up to 2 gigawatt-hours. The figure shown in this slide gives information regarding the origin of electricity on 7th February this year. This information is given by the webpage of Red Eléctrica. Red Eléctrica is the Spanish corporation that operates the national electricity grid in Spain. By focusing on the power generated by concentrating solar thermal power, it is evident that this technology continues to produce electricity after sunset. This is due to the fact that in Spain, approximately 80% of these power plants are equipped with thermal storage systems. Long-term systems for grid applications are key to making concentrating solar thermal technologies dispatchable. Since 2008, they have provided cost-effective solutions in Spain, offering much more competitive pricing when compared to other technologies, including electrochemical batteries. A cost range is indicated due to the varying temperature steps of the current system, with some operating at 100 degrees and others at 300 degrees. As previously stated, the stored energy density in sensible thermal storage systems is dependent on the temperature step applied to the storage medium. In any case, the cost is at least one-third of that reported for batteries. The concept of utilizing molten salt in separate tanks when they are hot and cold for long-term and long-duration energy storage can also be applied in industrial contexts. Several companies are offering systems that adopt the general approach here mentioned, but with specific designs. Molten salts differ from solar salt in that they can be used at temperatures below 240, which is the lowest temperature limit for solar salt. Pilot plants with links to a variety of industrial sectors are in operation at the present time. To conclude this presentation, please note that sensible thermal energy storage systems are commercially available for a variety of applications. In the context of domestic heating and industrial processes below 100 degrees, water is typically employed as a storage medium in a single tank. In the context of power generation, molten salt is the energy storage material of choice, with a two-tank configuration being employed. The cost of these systems is relatively low. The key drivers behind the development of Carnot battery concept are these thermal energy system capabilities in terms of their low cost, long duration, and long term. Carnot batteries convert power from non-dispatchable renewables such as wind or PV into heat. This heat is then stored in an energy storage system and converted back into power using a Rankine cycle or another thermodynamic cycle. The concept is referred to as the power to heat to power concept or as the power to heat to X concept for industrial process heat. For industrial processes requiring temperatures in excess of 100 degrees, there are pilot plants in operation that primarily utilize molten salt and multi-tank configurations, or solid bricks and air as heat transfer fluid. We are currently exploring a range of alternative configurations and materials to the ones mentioned above. That's it. Thank you for your attention. If you required any additional clarification on this general overview of sensible thermal energy storage technology, please do not hesitate to contact me. It is important to recognize that thermal energy storage is a crucial component of achieving a sustainable energy mix. Thank you.